Okay, so it's a great pleasure to present Sullivan from Stony Brook University, who will speak on 3D fluid motion.
Right. Okay. So, this is about Lefschetz Memorial Centenary. So I'm thinking algebraic geometry interpreted topologically, and then started this whole field of algebraic topology, really, at least by name. And it's called combinatorial topology before that. And then got into applied mathematics. Okay, so let's try to. So this talk is not so much about the first two, although it's there's a lot of influence, but it's more subtle, not explicit, implicit rather than explicit. But the idea is oh, good. I can read it like this. Okay, so let's say we're studying this equation, and we write an equation. This omega is a vector field on the, let's say, on a three-dimensional space. I'll take a compact three-manifold like T3. This is a vector field. It's called a vorticity. And it evolves according to the ideal fluid equation by, so write it two ways. Let's see. Oh, yeah. So it evolves according to some quadratic function of omega. I'll just write it like that. This is, omega is a vector field. And it has a name, it's called vorticity. It's sort of a very appealing topologically. It measures as the fluid is moving along, has its velocity, and the small particle of fluid or small region of fluid keeps the same volume, but it gets distorted. So a round thing would become an ellipsoid, and then this is turned at some speed. And this turning speed is the vorticity vector field. And this equation is, in words, is transported by the velocity of the motion. So this means instantaneously, you can sort of write a formula like this, it's the lead derivative relative to the velocity of the vorticity. But this vorticity is actually given as a function of the velocity. So it's the curl of the velocity. This is called Rot in German, right? So it's a rotation induced by the velocity, which is the instantaneous motion. And so there's actually an interesting formula. If we assume the velocity of the torus has circulation and zero in all three directions, then it's uniquely determined from the vorticity by an integral operator, which can write as B of omega, B of the vorticity is the velocity. So if you apply curl to both sides, curl B, then this is omega. So this operator B is the inverse of the curl operator. So curl of B of omega is omega, so is an inverse of. The topology is like this because curl is really exterior D, and D is like the prime direct line of D inverse, applied globally on the torus. Okay, so it fits very much with topology. Okay, and then, but let's not get into this too much. Now let's suppose you wanted to do some computations on a computer with this equation. You would somehow take these word sentences and discretize space, putting a grid down and writing approximations for the exterior derivative and its inverse, and write this out, and you would get, and you could do this. It's not too hard to do this and get a finite system of equations on the grid. And then the finite system of equations would have it'd actually be like a vector, how many 3 times the number of grid points. Would have like 1,000 in each direction, and you'd have 1,000 over 1,000 million times another 1,000 billion, and then times 3, so you'd have 3 billion components here. And then, and this quadratic function would come out to be just, so these would have indices alpha, and we would have quadratic functions in the components, a quadratic function in the component x1 up to 3 billion, right? Actually, that's kind of the limit of what computers can do, roughly on the order of 1,000. I mean, even with Microsoft or Google. Okay. Anyway, we get this equation, so I wasn't planning to do this at all, but then this, because of the conference, I was going to explain this point. So, you know, one day I had the idea in the early 90s, well, let's try to apply algebra to this equation. So let's just think of what's the general theory. Can you make some general theory of system of quadratic equations like this? And so I couldn't do very much. So one day I asked Dr. Gadler, 24 hours later, he gave me a beautiful argument, okay, which I will explain. I take half credit because I formulated the question and asked the right person. Right? So that's 2/3. Well, in this case, it's a half. It's really a brilliant argument. Okay, so hope you enjoy the argument. It's very easy. So first, being an algebraic geometer, he says, it claims, first of all, first claim is generically. So in algebraic geometry, you study every question, first you ask it generically, right? Right? Okay. And then generically, there are no zeros of the right-hand side. This is a vector of quadratics. Now, we're in algebraic geometers. Why is this? This is actually obvious once you say it. It took me a while to learn it. Let's see why. Because you have n quadratics. You want them all to be 0. Quadratics and n variables. So let's say you have 10, so let's say you have 10 equations, 10 components, 10 equations. So you're intersecting 10 quadratics in 10 variables. Well, that's 10 hypersurfaces in RP9. So each time you intersect, you go down by 1, and then generically you don't have any. So generically there are no common zeros. Okay. So that's generic algebraic geometry. Okay. So now we go to algebraic topology. So now you can consider a new equation. Let's consider the mapping from Sn minus 1 to Sn minus 1. So this is for all for really using springs, which is Q divided by the absolute value of Q. Q is like a vector. So if you're on the unit sphere, this bottom thing isn't ever zero. We just showed that, right? There are no common zeros. So we get a mapping from Sn minus 1 to itself. But it stands antipodal, this is quadratic, so it stands antipodal points on the sphere to single points on the sphere. Right? This Q of X is minus Q of minus X. Well, I mean, Q of X is equals Q of X equals Q of minus X, because it's quadratic, it's like X squared, right? So it sends antipodal points to single points. So therefore, if you took a generic point here, you would have an even number of pre-images. So the degree, we don't worry about the signs, the degree is even of this mapping. Right? So, and the sphere only has homology Z in degree 0. Now I'm doing atoms. No, I got Z in degree 0 and Z in the top degree. And the degree is even in the top degree. And the degree in degree 1 is 1. The connector space connected to the connector space. So the alternating sum of the traces of the action on homology is 1 plus or minus an even number. So the Lefschetz number is always non-zero. 1 plus or minus an even number is always non-zero. So L of F, it's great to get 2/3 credit for an argument like this. So L of F, this is graph F, is not equal to 0. So what does that mean? What? What? You have to speak up. What? Yes, there's a fixed point. So there's a ray in this billion-dimensional space, which is invariant under this quadratic map. And so the vector field, the differential equation, reduces to the equation x dot is ax squared for some a. There's some quadratic function on the line. And now, actually, I thought my clock was 2:30, so I'm out there at 10:20, trying to remember the formula for solution to this. Anyway, so, I can remember it and everything. So I'm trying to just solve this. X of t is minus, thing right. Oh, yeah. Minus 1 over at minus 1. Let's see if I can compute this. So take the derivative of x dot and get minus the derivative of 1 over x is minus 1 over x squared. Is that right? Okay. So minus a minus 1 over at minus 1 squared, which is equal, wait, I forgot the a, which is supposed to do differentiating. So I got a up here. Okay, so differentiate at gets a, right? Okay. So this is equal to a let's square this So the derivative d by dt of x of t is equal to this. We'll get it out. Oh, this a over, well, yeah, well, it's a times 1 over at minus 1 squared. Which is equal to a. Okay. All right, okay. So what does this mean? This means that when this solution continues until capital T equals 1 over a, and then it blows up, right? So this starts off, goes like that, right? So generically, so this is Locke-Gavrich. Okay, I write the name down. Locke-Gavrich proof. Anyway, I found out later that it's irrelevant that York has this famous paper in dynamics called something about 1, 2, 3 infinity. Period 3 implies chaos. Anybody heard of that paper? Yeah. Period 3 implies chaos. So he proved this same result. So 30 years before, I mean, so 20, I don't know, years before this. Okay, so this was in the 90s. It was he proved in the 80s or late 70s. But I found that out later. Okay. Anyway, so what is this? So we used applied mathematics, algebraic ecology, algebraic geometry, and electrostatic function. Okay. All right. So this sort of means when you try to take this equation and do a finite approximation, do computer study, generically it's blowing up. If you type this, well, this is a particular equation. This is all equations of this algebraic type. So maybe there are certain identities or certain geometric features that would allow you to escape this consideration. You're going to summarize it, right? But what is that subdividing? Or what is not that subdividing? Okay. So now we need mathematical structure. We want to analyze the mathematical structure of this equation to see whether it blows up or not. And this is not the famous equation in the what do you call these clay problems? If you add Brownian motion, if you add diffusion, then this is the famous equation. What are these called? Millennium problems, right? What are they called?
Navier-Stokes. Millennium problems.
No, I'm asking what the set of problems which I'm referring to is called.
Millennium problems.
Huh?
Millennium.
What? Millennium problems. Okay. So one of them is, does this equation, when you have diffusion here, with smooth data, stay smooth for all time? Diffusion is Gaussian term times a constant. Right? So, and but a lot of people have studied both equations over the years. This particular equation was written down by Euler in 1757 and said analysis isn't ready for this equation. And Navier was 1822 and Stokes was 1844 for different reasons. They looked at the one with diffusion, or they made it up. The idea was that the equation without the diffusion is called ideal fluid motion, is assuming there's no viscosity and it's incompressible. And then you can derive this equation, Newton's laws. But the particles of the fluid actually interact, they bump into each other. And this, if you randomize, if you think of averaging out these effects in all directions, that this Brownian motion diffusion, so Brownian motion was observed fluid motion, like air molecules floating around. So this is really Brownian motion. And for an analyst, this term helps. And it actually, when you get into the structure, it both helps and doesn't help. So it's not so clear, but you're hoping for a positive answer. You want the model to be correct. The fluids know what to do. So I think they chose this version of the problem to be the millennium problem. No, rather the one that might have a positive answer is more realistic. Okay. All right. One of our colleagues at Stony Brook, David Evan, in '68, showed that this equation is locally, for smooth data, well defined. But anyway, so if we just think of it algebraically, we get generically blows up in some directions. But one has to think about how to interpret these results. So, okay. Okay. So
Racing.
so now we want to look for some mathematical structure. This equation. And the idea is going to be very down to earth. It's all about 3 by 3 matrices. I'm doing 3D. So it's really all about 3 by 3 matrices, which we think we understand. But I've learned I don't understand nearly as much. The fraction I understand is below 10%. I used to think it was like 30 or 40%, but about 3 by 3 matrices. Okay. So let's see what's going on here. Okay. Oh yeah. So so the idea. Well, the mini idea is, let's just think of a 3-dimensional vector space. V is a 3-dimensional vector space. So I want to think of it abstract. I'm secretly thinking it's R3, but I want it to be abstract so that we could think in terms of structure, transporter structure, and so on. So these are 3-dimensional real bit vector space. Many ideas, we want to study the interesting space of all positive definite inner products on V. Okay, all positive definite inner products on V. Wow, we learned about this in first year algebra. You know everything about it, right? Not true. Okay. So this is an ellipsoid using the space of ellipsoids in V. And I want to later just take them up to the shape, up to rescaling. In fact, then I can choose ellipsoids of volume 1. Okay. So, but I want to allow myself to be ambiguous about which case I'm in, because without doing that normalization, it has slightly nicer symmetry. It's called the rule of 3. Now, what is this space of ellipsoid? So now let's talk about all ellipsoids without that consideration. For fluids, we want to take volume 1 or take up to scale. Quasi-conformal mathematics, technical theory, we take 2-dimensional ellipses up to scale. That's a big theory. Some of those ideas are lurking here also. Okay. And then, so this mini, the main point why this is called an idea, consider this is So what's the dimension of this space? The space of ellipsoids on a three-dimensional space. John. Hi.
Where's you?
Good morning. Good morning.
Where's you?
What's the dimension of this space, John? Three-dimensional ellipsoids.
Well, we have three numbers.
What?
We have the three numbers that give us the eccentricity of the.
Yes.
And then we have the orientation.
Right, okay, right. So he's, okay, so this is six-dimensional. Yes. Three parameters for this and three parameters for this, okay? And that's almost, well, that's why this is all about the numbers 3 and 6 and 9, actually. So 3 plus 3 and 3 plus 3 plus 3. So now this space is a non-compact space because the ellipsoid can be very long. It's not compact because of the scale, but that's not so interesting. It's not compact because the ellipsoid can be very long and narrow. And this is an example. So let me just write this down. I'll give the definition of this phrase, cartan symmetric space. Very, very beautiful. It's hard to forget. I remember the day when I asked this to Jack Cheater when I was a grad student. He told me, you know, can't forget this definition. And who knows the definition? Cartan symmetric space. You can just raise your hand. No, I'm not going to call it. Okay. No, it's very beautiful. It's a complete metric space, manifolds, and it has the property at every point. There's an involution that fixes the point, and around the point is the antipodal map on the tangent directions. At every point you have such an involution. And then the picture you can't forget is the proof that if you take any path in this space, you can flip along the path, flip it over, move a little bit on, choose a point on the path a little further in, flip from there, flip from there, flip from there, and you can move along and build an isometry that goes from any point to any other point. So it's a homogeneous space. Just for this definition, you get it from it. So usually you say homogeneous spaces are blah, 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 you know, but here you get it by an argument. And also this mapping, this is famous argument of somebody whose name I forget, I wish you could remember it. This also shows the parallel translation associated to any metric that has this property for these involutions must be given by this motion along paths. This is also a parallel translation of the metric. So you get this homogeneous, you see explicitly what parallel translation is, the Levi-Civita connection, blah, 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 right? Okay. So this, and these were synonymous with, you know, his thesis is a cartan. In his thesis, he classified Lie algebras, finite-dimensional, simple Lie algebras over C, and then later he did them over R. And then these symmetric spaces turn out to be the Deus ex machina, or parallel, purely geometric object that corresponded to the classification of all the Lie groups. So this is sort of the geometric essence of the classification of Lie groups. There's some combinatorial aspect to this, which I'm trying to learn now myself, but they're quite beautiful objects. And they also have, so for example, there's the hyperbolic spaces are symmetric spaces, Euclidean spaces are symmetric spaces. The sphere are compact symmetric spaces. So this is a non-compact symmetric space. So it's a generalization. So this 6 manifold is really S6. This of all ellipsoids is really the reals cross S5, where this is the scale of the volume. Okay, so I'm kind of usually interested in this S5, but I'm still going to talk about S6. Okay, but for the fluid thing, I have to focus on the S5, but we'll really get that far. Okay. But anyway, this is the mini idea. And then this is the local, what's the mini as in local somehow. Point-wise, functional. Not in any way, but point-wise. Okay. So then I want to consider all metrics, all smooth metrics on T3. And I'm going to replace the fluid motion by a motion on this space of the metrics, the moduli space of all metrics. It's not even, I don't have to say moduli space, it's just the set of all metrics, smooth metrics on this. Because there are only a few automorphisms, so I can understand everything at once. So what is this? This means you associate, well, you can associate, here's T3, since it's parallelizable in a natural way, it has affine connection, flat connection. We can move these ellipsoids. If we have an ellipsoid at one point, we can move it around to any other point. So we have a bundle of S6s up here. And this bundle is actually naturally a product bundle, right? But then you can think of a section of this bundle, a smooth section, as being a metric. So it associates to each point an ellipsoid. Okay? And so this is mass. This is all smooth mass of T3 into S6. It's a cross section is like, this is the graph of a map from here to here, right? And this is a nice thing, infinite dimensional spaces that are maps of some compact manifold into some other finite dimensional manifolds. They inherit all of the structure of the maps, inherit all the structure of the domain. If this is a group, this is a group. If it's a Lie group, a Lie group. Right, infinite dimensional version. So it's very natural to do that. So the space of all metrics is naturally, what is S6? It's one of these cartan symmetric spaces. Naturally symmetric space. And it's clear because if this is one metric, at each point, the fiber has a point and there's an involution of S6 that fixes that point. So you take all of these different involutions acting vertically, and that gives an involution that fixes this whole metric and takes another metric like that, another. So the cartan symmetric space. Oh, what's the metric on the space of all metrics? I forgot that step. It's wonderful. It has the tautologous metric. Has I've used this word tautologous metric. Because what is an ellipsoid? I mean, what is a metric at a point? It's a symmetric tensor in an open set, or it's positive and non-degenerate, right? Non-degenerate and positive, right? So it's an open set of the 6-dimensional space of inner products. And then a tensor is given, a metric is given by a tensor, but if you have a metric, then you can measure the tensors on the vector space. You have a metric on the vector space, a tangent space at a point, at every point. Then you can measure a symmetric tensor length. So it's like the trace of the square of the matrix. That would give you the sum of the squares of the eigenvalues. Anyway, so there's a canonical metric that's autologous metric. And that's the one that we're using on each fiber as well. Okay. So this is a symmetric space. And there's something here. Well, what's that? Okay, so. Okay, so let me. Okay, so now the goal to avoid this fact that things blow up, we had over there. The goal is to take this differential equation that I'm studying, the ideal fluid motion, and the goal is to get try to find a priori balance on how the flow is evolving. And the way I'm going to think of the flow, I'm going to measure the flow by studying how it distorts the metric as it flows along. So how does it distort the metric? So I'm going to consider this flow. This is the flow of the fluid. And I'm going to start at time 0. And I'm going to suppose I have up to time t, time 0, I have this solution to this equation. The David even says that I have it for a little while. And Euler, Leray had a beautiful theorem too from 1934 about solving this. But there are many topologies, and depending on how smooth you take things, and you'd like to have some topology where you have unique existence and uniqueness for all time. That's the big goal. So let's start with the smoothest topology, and even you can imagine real analytic because it's another question. That's it. I'm wandering here. So I want to study this, and I want to think of the background metric and the G for metrics, Brownian metric. I put that at time 0, and then at time here, this is the flow, but I'm going to let GT be the transported metric by the fluid motion, which is time t. Okay. Does that make sense? Transportive structure. Okay. And as the fluid motion gets more and more complicated, this metric it becomes more and more or less known. But now there's some interesting things like the tautologous metric on the space of metrics. So we can draw a diagram like this. We have G naught, and then we have some GT at time t, and we can, symmetric spaces of this type are, this S6 is what's called a Hadamard space. It has curvature between a negative number and 0. So it has unique geodesics between any pairs of points. Hadamard space. And Cartesian, and this is sort of like Cartesian product of those. So it'll have a similar property. It'll have metric, non-positively curved at every point. So you have unique geodesics. So I'm drawing the geodesic in the space of metrics. This is the symmetric space of metrics. And now, remember the equation we're studying. Did anyone remember a sentence about what it means? A sentence for that? Remember? See, I only like equations if they have sentences that describe them. So that's why I've studied this since the 90s. This says the vorticity vector field is actually transported by the motion to a vector field, which is the vorticity at time t of the motion. So the curl of the motion is transported by the motion. Right? It was W dot is the lead derivative with respect to the vector velocity field of W. That was the equation. Okay. But velocity is the uncurl of vorticity, so it's quadratic in its way. Okay. The quadratic equation there. Okay, so the equation is, so you could study, well, let's study how, what, prove something? Oh, yeah, right, prove something, yeah. Right, so let's make sure of that now. Okay, 15 minutes, okay. So I learned this trick from a TIA. You said, I just wondered why, I should be saying this, why I applied this to T and bot, and I'll tell you afterwards if anybody wants to know privately, okay, why each one gave good lectures for different reasons. Okay. But it's very relevant right now. Okay. So the interesting thing about these symmetric spaces, they're called symmetric spaces of higher rank, is they have interesting, well, even hyperbolic space, which has rank 1, has interesting one-dimensional flat subspaces, the geodesics. But these higher rank spaces, like S6 has rank 3, it's got three-dimensional subspaces that are totally geodesic and intrinsically Euclidean. Okay, so you have lots of flat subspaces all over the place. And the way they're configured and so on is what I'm trying to understand better now. But, you know, this Keats did a lot of amazing work that explained combinatorially what goes on for these symmetric spaces. And even over the local fields. So, just over the fields. So, oh yeah, so these flat subspaces. So here's an example. So if you take, so what is this? Let me say what it is for S6. So take a point in S6. That's a point, right? In S6, namely it's an inner product on the vector space V. Right? That's a point. And let's suppose it has these three axes, generic, as three different axes. Then you can just take the diagonal matrices and stretch in all possible directions. You've got a three-parameter subspace of ellipsoids that share the same axis system. That will be a submanifold of S6, which is intrinsically flat and totally geodesic. So that's a cool fact. Okay, and now, so let's suppose the vorticity at time 0 looks like this, and then it's being transported to time t. Well, the axes is going to have the same three ratios, and the axes are just transported to the axes. So this is the way the metric, this is, sorry. Let's skip a step. So here I'm looking, when I draw this picture with the axes, you actually have to, this is the distortion of the metric at a certain point by the vorticity at time 0, the vector field. It's distorted. So I'm supposing, you know, the metric is round and then it instantaneously is distorted in this way. That's what I'm assuming. And this distortion, if the vorticity vector field is transported to the vorticity vector field, this distortion, which is by, you know, French high school transport of structure. If you transport the metric and the vector field, the distortion will just be the transported distortion, a transported structure. Okay, so that means the distortion of GT by omega t is the same as the distortion of G0 by omega 0. So this is the invariance principle for studying this flow, which, you know, so you can know. I'm done. I'm going to just prove something now. Write down some formulas. Okay, so let's see. So we take this geodesic And, well, at time zero, we have a smooth thing on the torus. It does something to this G naught. Omega zero is distorted somehow. Something. Just big O of one. It's on order one. It's compact space. Smooth order one. Is the initial data. So it's some constant. Bounded by some constant. It's just some particular thing. So, but then if you let time evolve, the metric evolves, the vorticity is transported, the metric evolves by transport, the distortion stays the same thing. So, so we get for each time and for each point this way. This is I could do this at each point in T3, and for each time. I think of this discussion, and then I get at each point I get this flat subspace generated by this picture here, and then as I move along, I get different flat subspaces. I move this way, I get different flat subspaces. This is the distortion of G naught by W naught. At this point, this is the distortion. At this point, and just move along in time, and this is. I'm drawing one picture on top of the other. This is in the space of fields. So I'm just drawing this as one thing. So I have the field of structures, and then I'm putting them all together in geodesic. And this flat subspace is transported along at every point. So I'm going to take the inside this space of metrics, which is evolving under the flow. I'm going to also move the time t ends and the time zero ends by using the mapping, the motion in time capital T. This, so I get a circular thing. I'm trying to get an a priori bound on from the motion on this interval 0 t. So I'm going to, if you have an interval, move the two ends together, get a circle. So then you get a circular construction in infinite dimensions, and there's some kind of invariance going along in the symmetric space of all metrics, and the distortion is described by this transporter structure. And so, at time zero, everything is smooth, so this is just some fixed distortion that varies in a smooth way on a compact manifold. So, and this symmetric space is like a product. You know, when you write mass of x to a y, you write x to a y. Why is the x? It's like a product, right? So you can think it's intuitive like a product. Technically, you have to treat it slightly differently, but intuitively it's like a product. And so you put you have a natural Riemann metric at each point in each direction, and you take the L2 norm of this to give a metric on the whole field. So, and this is all staying in this flat subspace. The flat subspaces are transported along by the motion. That's the equation. So I take the product of all the flat subspaces to some big flat Hilbert subspace of S sub m, the symmetric space of all metrics. So I'm getting a big Hilbert space of flat subspaces inside the symmetric space of all metrics, which is, and then I glue the ends together, T, capital T, 0. And then I get a motion on this, which preserves this flat subspace. It just cyclically permutes all the factors. So that's the kind of main idea, is to try to protect the motion on this symmetric space, which has negative curvature, which kills any decent a priori estimates to try to stay away from the negative curvature by keeping the motion inside a flat subspace. So this is a bit technical, I'm not going over it too fast. Not technical, but it's tricky. So, okay, so there's kind of an argument now. Let me erase the irrelevant stuff from here. Well, now that was to this. I'm back in the metric space of all metrics, and inside this big flat subspace inside the metric space, the space of all metrics, and silver space. I remember being relieved when I was trying to learn in math about Hilbert space and stuff. Heck, it's just Euclidean space, right? Hilbert space is just Euclidean space. Every bunch of vectors, you can draw triangles, you know, like high school geometry. Okay. So now we're going to use that right now. We're back in high school. So here's this path. This is this unknown metric. I don't know where it is. I don't know how long this path is. I'm going to give it a name, R sub T. And so this is going to be proposition 1. And then there's going to be a proposition 2, which I don't have yet, and what I'm working on. This is related to that question I want to ask you. Okay. So the proposition 1 is okay. So let's just sort of go back away from this all and think, now what's going on? I'm doing something evolving, but I have this word sentence. PDE is a word sentence. The vorticity is transported by the motion. To get something out of that, I also transport the metric. So then I get the distortion of the moving metric by the moving vorticity is the same. It's just repositioned in space. As you transport two things the way they interact, their interaction is transporters. The tautology. Okay. So then this is some unknown thing, but notice that time, this is distortion of omega t, this is distortion of omega 0 here. I'm interested in how does omega t distort the background metric. I want to get an a priori bound. Omega t is unknown. I don't know how does it distort the background metric. That's when you write derivatives of something, that's what you're getting. Okay, well now omega t distorts the moving metric the same way omega 0 distorts G0. So therefore, this just moves like O of 1. Omega t distorts G of t by something on the order of 1. Be constant. Because it's the same way G0 is distorted by omega 0, the size. But that's sort of the moment, okay? A moment, okay? Get that? This is transported structure. If something is transported and it interacts with something which is also being transported, that interaction is transported. But definition of transported structure, which they learn in French high school. Okay. All right. So, as Americans, only certain Americans know it. All the algebra founders know it, but I mean, PDE people don't know transported structure. If you say any example, they, yeah, of course. Anyway, okay. The whole point of this is transporter structure. Okay. And now every vector field, and I think of doing this vector field for a small amount of time, delta t. So it's a small motion. And I want to see how this stuff is evolving under small motions. Okay, so what does it look like? It's all happening inside this Hilbert space because the distortion is defined as these flats, and the different flats defined is using the omega distortion of time t. They're at the end, and also it's invariant under the motion because of the rule. So what's happening? If this is I'm worried about this being a very big number. So just back away from it. Back away from it. And this very long, just back away from it, then this long thing is still long, but this short thing becomes minuscule, right? You back away from something, you have a little stick here, and one going over here to, back to New York, okay? And the stick gets long, you get up in an airplane, like a rocket ship, and look down. So this, the distance from here to New York is right 1. This small stick is 0 length. Okay. So looked at that way, this is just an isometry that fixes this point. The small motion is an isometry that fixes this point. So it's just a rotation about this point, more or less. You have to add a little bit, but intuitively it's a rotation. And so this just, and the angle here will be proportional to this speed of rotation, delta t. And so there's a constant here, which I'm not going to write, but then this distance that it moves, it's like you're in the plane. I mean, not an airplane, but in the Euclidean plane, and you're just going like this. The distance you move is proportional to the length times the angle. So you get an inequality that omega t distorts the distortion of G naught on omega t is less than or equal to delta t times RT. And there's some constant there, right? Okay. That's proposition 1. Okay. Proposition 2, I don't have the proof of yet, but the idea would be, I had the proof when I lectured on it at school, but I realized the constant, here I have control of the constant, that it isn't right. You can have control of that. That's another argument for some minute because of time. Oh, gosh, I'm over. Anyway, you have to do the same picture and now try to understand how the velocity distorts this picture. Well, you know you're moving along this way by the vorticity. In this formula B that I had before, uncurling, is an interval operator and it reduces the global effect of V is smoother than omega. So there is a known constant that will convert this inequality to a corresponding inequality for how this point moves. For the analysts in the audience, the Quatermain-Zygmunt operator applied to the distortion of the vorticity of G naught is smoothing border 1, it decreases the way the velocity distorts G naught at t. And that's the equation. I mean, the curl of the vorticity, the uncurl of the vorticity of the velocity. Okay. So this is on the order of delta t times r sub t. And now, so what's an isometry? See, this is still Euclidean space, this Hilbert space. So I want to know how, so here's this point, we're moving along. If there were no rotation, I would just get, again, the same estimate. But actually, this point is moving along. There's also, as I move along, there's some rotation. So there's another, so I'm moving and at the same time I'm rotating. That's what an isometry of Euclidean space is like. Translation and rotation, right? So there's a rotation here. So you get, so this is sort of, I want to study how VT distorts GT because the whole motion is at the point GT. VT, the instantaneous motion is distorting GT. The GT plus the delta T. And then the next one is distorting into GT plus again. So I want to estimate how GT is distorted by the velocity. So G0 is being distorted in a controlled way because of proposition 1 by the velocity and this more operator. But now there's this rotation, and so I get so this is, if I move a little bit, there's a little bit of rotation here. And then as I move, there's a little bit more rotation, there's a little bit more rotation. So you get a kind of inequality, which is so this is delta T of RT. See, RT is what I don't know. And then this has to be added to plus RT times this rotation effect. And this is all times moving for delta T times the constant, which is what's this angular speed of the rotation part of the VT motion. So, except for this constant, I would get, if I could ignore the constant, I would get RT, and so, well, I have to do the algebra here, but I get RT delta T and I get delta T squared, so it's related to some second order equation, but it's explicit. And right now I'm struggling with getting control of the constant. And well, we'll stop there.